Welcome! Today, we're diving into LeetCode problem number 936, stamping the sequence. This problem challenges us to find the sequence of moves to transform one string into another using a stamping operation. We'll explore the optimal approach, its implementation, and the reasoning behind it. Let's get started. In this problem, you are given two strings, a stamp string and a target string. The goal is to repeatedly stamp the stamp string onto the target string until the entire target becomes a sequence of question marks. Now, how does the stamping process work? You can place the stamp string at any valid position within the target, as long as the stamp fits entirely within the bounds of the target. When you stamp, each character in the stamp string replaces the corresponding character in the target string. However, there's one important restriction: if any character in the stamp string doesn't match the corresponding character in the target string, the stamping operation is invalid. Once a stamp is applied, all characters in the stamp string, whether they matched before or not, will replace the target characters, even if some of those were already question marks. You can repeat this process multiple times, including overlapping stamps if needed, to eventually convert the entire target into question marks. Your task is to return an array of the positions where you stamped, listed in reverse order of the operations. If it's not possible to stamp the entire target into question marks, the output should be an empty array. The input to this problem consists of two strings: the stamp string, which contains only lowercase English letters and has a length between 1 and 10, and the target string, which contains lowercase letters and may also include question marks. The target string can be as long as 10,000 characters. The output is an array of integers that represent the indices where the stamp string was applied to the target. These positions must be listed in reverse order, corresponding to the sequence of stamping operations. If it's not possible to stamp the entire target into question marks, the output should be an empty array. Let's look at a concrete example to understand this better. Suppose the stamp is ABC and the target string is a BAC. The expected output would be 0, 2. Here's how the stamping process works for the previous example. First, we stamp ABC at position 0 in the target string. This converts the target from a BAC to BC. Next, we stamp ABC again, but this time at position 2. The target now becomes? Since the entire target string has been turned into question marks, we can return the positions where the stamps were applied, but in reverse order. So, the output is 0, 2. Another example involves the stamp ABCA and the target ABCACA. The expected output in this case is 0, 3, 1. Let's break it down step by step to see why. For the second example, the stamp ABCA is first applied at position 0, which transforms the target string from ABCACA to CACA. Then, we stamp ABCA at position 3, further modifying the target to A. Finally, we stamp ABCA at position 1. This completes the transformation, turning the target into? The positions of the stamps, in reverse order of application, are 0, 3, 1. These examples demonstrate the expected output format and the logic behind stamping. Now, let's consider some important constraints and edge cases for this problem. Your solution needs to be efficient, especially since the target string can be very large, up to 10,000 characters. A naive solution with a time complexity of n squared may not work well for longer inputs, so aim for an optimized approach. Additionally, the problem guarantees that if a solution exists, there is at least one valid sequence of stamping operations. However, there are specific edge cases to consider. For instance, if the stamp is longer than the target, or if the stamp cannot match any part of the target, the output should be an empty array. Similarly, if the target is already all question marks, no stamping is needed, and you should return an empty array. Finally, stamping remains valid even if some characters in the target are already question marks, as long as the other characters match. These constraints and edge cases will guide you as you design an efficient solution. To solve the problem of stamping the sequence, our goal is to identify the sequence of indices where we can apply the stamp to transform the target string completely into question marks. This is a reverse simulation problem that requires careful consideration of dependencies between replacements. One straightforward approach is the brute force method. Here, we iterate over the target string, looking for valid positions where the stamp can be applied. At each valid position, we replace the corresponding substring with question marks and record the index of that operation. This process continues until either the target string is fully transformed into question marks or no further progress can be made. While simple, this method is computationally expensive, as it involves repeatedly scanning the target string. The time complexity is proportional to the product of the lengths of the target and stamp, multiplied by the number of replacements. Additionally, this approach does not effectively handle dependencies between replacements, making it less efficient for larger inputs. To address the inefficiencies of the brute force method, we can use an optimized approach based on reverse simulation. Instead of simulating the stamping process in a forward direction, we simulate it in reverse. This means starting with the target string filled with question marks and reconstructing the original target by unstamping the stamp at specific positions. This approach avoids redundant scans and ensures that dependencies between stamping operations are handled systematically. A key observation here is that each valid stamping must replace at least one non-question mark character in the target. By maintaining a queue of positions where the stamp can be applied and tracking visited positions, we systematically reconstruct the target. If the reconstruction is successful, we return the sequence of indices in reverse order. Otherwise, if no progress can be made, we return an empty array. The time complexity of this method is linear with respect to the product of the lengths of the target and stamp, making it significantly more efficient than brute force. This approach is both systematic and aligned with the problem's constraints. Another theoretical approach involves modeling the problem as a graph. Here, each node represents a substring of the target, and edges represent valid transitions where a stamping operation can occur. Using a graph-based approach, we could perform a topological sort to determine the sequence of stamping operations. However, this method introduces unnecessary complexity. Building the graph and traversing it are computationally expensive tasks, and the approach does not provide any significant advantage over reverse simulation. Given these drawbacks, the graph-based method is not a practical choice for this problem. Instead, we find that the optimized reverse simulation approach is the most suitable. It provides clarity, ensures systematic handling of dependencies, and avoids the inefficiencies of brute force while being far less complex than the graph-based alternative. When comparing the different approaches, there are important trade-offs to consider. The brute force method, while straightforward, involves repetitive scanning and is inefficient for large inputs. In contrast, the optimized approach minimizes redundant computations and systematically handles dependencies, making it far more practical. Reverse simulation, as used in the optimized method, is particularly effective because it reconstructs the problem in a way that naturally manages dependencies, unlike forward simulation, which can be harder to control. Finally, while the graph-based approach is theoretically interesting, its complexity makes it less practical for this problem. By choosing reverse simulation, we achieve a balance of efficiency, clarity, and systematic problem-solving, making it the optimal strategy for solving this challenge. To begin, the problem stamping the sequence asks us to transform a given target string into a sequence of question marks by repeatedly applying a given stamp string at specific positions. The objective is to determine the sequence of indices where the stamp is applied, ensuring that the entire target string is eventually reduced to question marks. If it's not possible to achieve this, we return an empty list. Importantly, this is a reverse engineering problem. Instead of constructing the target string by applying stamps, we simulate the process backward, focusing on erasing the target string step by step into question marks. Now, let's break the algorithm into clear steps. First, we define the problem in reverse terms. Rather than building the target, our goal is to reduce it to a sequence of question marks. Every stamping operation replaces a substring of the target with question marks, but only if the substring matches the given stamp or contains question marks where the stamp could fit. The task is to determine the sequence of these stamping operations in reverse order. We adopt a greedy approach here by repeatedly finding positions where the stamp can be applied in reverse. This involves identifying substrings that either match the stamp exactly or have question marks in positions that the stamp can overwrite. Once we find such a valid position, we replace the substring with question marks and record the index. Finally, we continue this process until the target consists entirely of question marks or conclude that it's impossible if no valid positions exist during an iteration. After completing the stamping process, we need to return the sequence of indices in forward order. Since we simulated the stamping in reverse, the indices are collected in reverse order, so we simply reverse the list before returning it. To implement this, we define two helper functions. The first is can_stamp, which determines whether the stamp can be applied at a given position. This function checks if the substring at that position exactly matches the stamp or if the substring contains question marks where the stamp can still fit. The second helper function is do_stamp, which performs the stamping operation by replacing the substring with question marks at the given position. These two functions are core components of our solution. The main algorithm proceeds with a greedy reverse simulation. We start by initializing an empty list called result to store the indices of successful stamp applications. We also use a Boolean array called visited to track positions that have already been stamped, preventing redundant checks. Then, we iterate through the target string, checking for valid stamp positions. At each valid position, we apply the stamp, mark it as visited, and add the index to the result list. This process is repeated until either all characters in the target are question marks or no valid stamp positions remain. To handle edge cases, we ensure that if the target cannot be fully reduced to question marks, we return an empty list. Additionally, we account for scenarios where the stamp is longer than the target, which makes it impossible to proceed and requires returning an empty list. Once the target is fully reduced, we reverse the result list and return it. There are several key insights that make this algorithm effective. First, the reverse simulation approach simplifies the problem by focusing on erasing the target instead of constructing it. Second, the greedy strategy ensures that we always make progress by applying the stamp at the earliest valid position. Third, efficiency is achieved by using the visited array to avoid unnecessary checks and by focusing only on valid stamping positions. Finally, handling edge cases like mismatched characters or an empty stamp ensures robustness. To support this process, we rely on two primary data structures, a Boolean visited array to track stamped positions and a result list to store the indices of successful stamp applications. These indices are then reversed to produce the final output. Let's analyze the time complexity of this approach. The can_stamp operation, which checks if the stamp can be applied at a given position, takes k time, where k is the length of the stamp. Since each character in the target string is checked at most once during the stamping process, the overall iteration over the target string takes n time, where n is the length of the target. Combining these, the overall complexity of the algorithm is n*k, which is efficient given the problem constraints. To illustrate, consider the example input where the stamp is ABC and the target is a babk. Initially, the target is a babk, and the result list is empty. In the first stamping operation, we apply the stamp at index 2. This transforms the target into a b, and we add index 2 to the result list. Next, we apply the stamp at index 0, which fully erases the target, turning it into. We then add index 0 to the result list. At this point, the result list contains 0. Finally, since we collected the indices in reverse order, we reverse the list to get the final output 2. This represents the sequence of indices where the stamp was applied to successfully transform the target into question marks. Here, we define a class solution and implement the method moves_to_stamp, which takes two strings, stamp and target. The goal is to determine a sequence of moves to stamp out the target string. First, we calculate the lengths of stamp and target, store them in m and n, and convert both strings into lists for easier manipulation. We also initialize an empty list result to store the indices where stamping occurs and a visited list to keep track of which positions in the target we've already processed. Next, we define a helper function can_stamp that checks if the stamp can replace a substring of the target starting at a given index. This function loops through the characters in the stamp and compares them with the corresponding characters in the target. If all characters match, or the target position is already replaced with a, it returns true as long as at least one character can be replaced. If there's a mismatch, it returns false. Another helper function, do_stamp, modifies the target by replacing the characters in the matching range with. We then use a while loop with a changed flag to repeatedly identify and stamp valid segments of the target. Inside the loop, we iterate through all possible starting positions where the stamp could fit, checking if the position is unvisited and valid for stamping using can_stamp. If a valid position is found, we mark it as visited, set change to true, apply the do_stamp function at that position, and append the starting index to the result list. This process continues until no more changes are made, meaning no further valid positions for stamping exist. After exiting the loop, we check if the entire target string has been replaced with question marks. If true, we return the result list in reverse order, as the stamping must be applied from the last operation back to the first. If not all characters in target are replaced, it means the stamping sequence is invalid, and we return an empty list. This ensures the method returns the correct sequence of moves or indicates that it's impossible to stamp out the target string. Here, we start by defining the method moves_to_stamp, which takes two strings, stamp and target. The goal is to determine the sequence of moves needed to transform the target string into a sequence of question marks by repeatedly stamping substrings that match the stamp. First, we calculate the lengths of both strings and convert them into character arrays for easier manipulation. We also define a result list to store the indices of the stamping operations, a visited array to track which positions in the target have already been stamped, and a changed flag to indicate whether any changes were made during an iteration. Then, we use a while loop that continues as long as changes are being made. Within this loop, we iterate over all possible starting positions where the stamp can fit within the target. If the current position hasn't been visited and the canStamp method determines that stamping is possible at this position, we mark this position as visited, update the changed flag to true, and perform the stamping operation using the doStamp method. The starting index is then added to the result list. Finally, before exiting the loop, we check if all characters in the target array have been replaced with question marks. If not, we return an empty array to indicate that the transformation is not possible. Once we verify that all characters in the target array are successfully replaced with question marks, we reverse the result list to ensure the moves are returned in the correct order, as the stamping process works backward. We then convert the list to an integer array and return it. Now, let's look at the helper methods. The canStamp method checks whether the stamp can be applied to the target starting at a given position. It iterates through each character of the stamp and compares it with the corresponding character in the target. If a mismatch is found, it returns false. If all non-characters match, and there's at least one character that can be replaced, the method returns true. The doStamp method performs the actual stamping operation, replacing all characters in the target within the specified range with question marks. This is done by iterating through the range and assigning to each position. Together, these methods ensure that the stamping process is applied efficiently and correctly to achieve the desired transformation. To solve the problem, we begin with a basic example where the stamp is ABC and the target is a BAC. First, we initialize some variables. The length of the stamp, M, is 3, and the length of the target, N, is 5. We convert both the stamp and the target into lists of characters for easier manipulation. The result list will store the indices where we apply the stamp, and the visited array tracks whether we've already stamped at a particular index. Now, we start the main process by iterating over the range where stamping is possible, which is from index 0 to 2, since the stamp length is 3. This outer loop ensures we systematically check every possible position in the target where the stamp might fit. At the first position, I equals 0, we invoke the can_stamp function to check if the stamp can be applied. This involves comparing the substring of the target from index 0 to 3 with the stamp. Since they match, we proceed to apply the stamp by calling do_stamp 0. This replaces the relevant portion of the target with question marks, resulting in a new target of A, B, C. We also update the result list to include the index 0 and mark visited 0 as true. Next, at I equals 1, the can_stamp function determines that the stamp cannot be applied because the substring from index 1 to 4 does not match the stamp. We skip this index. Finally, at I equals 2, we find another match. We apply the stamp again, replacing the substring at index 2 to 5 with question marks. The target now becomes and we update the result list to include index 2, marking visited 2 as true. After completing the first pass of the outer loop, we check for any further possible changes, but since the target is now fully stamped, we exit the loop. In the final step, we confirm that all characters in the target are question marks, indicating that the stamping is complete. The result list, which currently stores the indices in the order they were processed, is reversed to provide the required output order. In this case, the output is 2, 0, which represents the sequence of stamp applications from the last to the first. This concludes the first example, where the stamping process was straightforward with no overlaps. Now, let's consider a slightly more complex example with overlapping stamps. Here, the stamp is ABCA and the target is ABCACA. We start by initializing the variables. The length of the stamp, M, is 4, and the length of the target, N, is 7. The stamp and target are again converted into lists of characters. The result list is empty, and the visited array is initialized with all values set to false. During the first pass of the outer loop, at I equals 0, we find that the substring from index 0 to 4 matches the stamp. We apply the stamp, replacing the corresponding portion of the target with question marks. The target becomes question mark, C, and we add index 0 to the result list, marking visited 0 as true. For the subsequent indices, from 1 to 3, no matches are found, so we skip those positions. When we reach I equals 4, we perform another check with can_stamp. This time, the substring from index 4 to 7 partially overlaps with the previous stamp but still matches the stamp completely. We apply the stamp again, replacing the corresponding portion of the target with question marks. The target now becomes question mark, indicating that the entire target has been stamped. We update the result list to include index 4 and mark visited 4 as true. After completing the first pass of the outer loop, no further changes are possible, so we exit the loop. In the final step, we confirm that the target is fully stamped, and we reverse the result list to provide the output as 4, 0. This demonstrates how overlapping stamps can still lead to a valid solution. In this example, we explore a case where stamping is not possible. The stamp is ABC, and the target is ABDAB. We initialize the variables as before, with M as 3 and N as 5. The stamp and target are converted into lists of characters. The result list is empty, and the visited array is initialized to false for all positions. As we iterate over the range of possible starting indices for stamping, from 0 to 2, we find that none of the substrings in the target match the stamp. At I equals 0, I equals 1, and I equals 2, the can_stamp function returns false, so no stamps are applied, and we skip each index. After completing the outer loop, we verify the target to check if all characters have been replaced with question marks. In this case, the target still contains characters other than question marks, meaning that stamping is incomplete. As a result, we return an empty list, indicating that it's not possible to stamp the target with the given stamp. This example highlights the importance of verifying whether the target can be fully stamped and serves as a reminder that some inputs may not have a valid solution. To analyze the time complexity of the solution, we break it down into its core components. First, the outer while loop is controlled by the changed variable, which ensures that the loop continues until no more stamping operations can occur. In the worst case, each character in the target string is stamped exactly once, so the while loop can run at most n times, where n is the length of the target. Inside the while loop, we have an inner for loop that iterates over all possible starting indices where the stamp could fit within the target. For a target of length n and a stamp of length m, there are m plus 1 such starting positions, making the inner loop run O, and m plus 1 times for each iteration of the while loop. Within the inner loop, the can_stamp function determines if the stamp can replace a substring of the target. This involves comparing up to m characters, making each call to can_stamp take O, m, time. Similarly, the do_stamp function replaces up to m characters in the target width, which also takes O, m, time per call. Now, combining these components gives us the overall time complexity. The outer while loop runs up to O, n, times. During each iteration, the inner for loop runs O, and m plus 1, times, and within that loop, the can_stamp and do_stamp functions each take O, m, time. When we multiply these factors together, the worst-case time complexity becomes O, n, asterisk O, and m plus 1, asterisk O, m, which simplifies to O, n squared asterisk m. Shifting focus to space complexity, the target and stamped strings are converted to lists for mutability, which requires O, n plus m, space. Additionally, there are auxiliary data structures like the result list, which stores the indices where the stamp is applied. In the worst case, this list can hold up to O, n, m plus 1 indices. Another auxiliary structure is the visited array, a Boolean list of size n used to track process starting indices. This requires O, n, space. Continuing with space complexity, the visited array adds O, n, space, and since no recursion is used in the algorithm, the call stack does not consume any additional space. Therefore, the overall space complexity sums up to O, n plus m plus, and m plus 1, which simplifies to O, n plus m. Let's compare this with the brute force approach. A naive solution would try every possible placement of the stamp in the target without optimization. This would involve testing every substring of length m in the target and simulating all possible stamping operations, leading to a time complexity of O, n squared asterisk m squared. The solution we're discussing is far more efficient because it uses the visited array and the changed variable to avoid redundant operations. This optimization reduces the time complexity to O, n squared asterisk m, while keeping the space complexity at O, n plus m. The optimized approach we've implemented strikes a practical balance between efficiency and simplicity. By using a greedy algorithm, it iteratively replaces valid substrings of the target with, avoiding the exponential overhead of the brute force approach. Let's examine the best, average, and worst-case scenarios for this solution. In the best case, the stamp matches the target perfectly in a single pass. This means the while loop runs only once, giving the time complexity O, n asterisk m. In the average case, the structure of the target and stamp typically requires multiple iterations, leading to a time complexity closer to O, n squared asterisk m. Finally, the worst case occurs when the stamp needs to be applied at every possible position in the target. Here, the outer while loop runs up to O, n, times, processing up to O, and m plus 1, starting indices in each iteration, and each operation takes O, m, time, which results in the same O, n squared asterisk m, complexity. This complexity arises from the combination of the while loop, the for loop, and the can underscore stamp and do underscore stamp operations. The space complexity of the solution also holds steady at O, n plus m. The target and stamp lists contribute O, n plus m, space, while the auxiliary arrays, such as the visited array of size n and the result list, add O, n, space. Importantly, the algorithm does not involve recursion or other dynamic memory allocations, so no additional space is used by the call stack. By carefully balancing time and space efficiency, this approach offers a significant improvement over the brute force method, delivering a much more practical solution to the problem. When working on the stamping the sequence problem, there are a few common mistakes to watch out for. First, not considering overlapping stamps can lead to problems. Since a stamp can overlap itself in the target string, failing to account for this can result in incorrect or suboptimal solutions. To address this, pay close attention to how overlapping regions are handled when reducing the target. Another frequent issue is ignoring the stamp reversal process. If you don't reverse the stamping process and work backward, you may end up with invalid or inefficient solutions. By tracing your steps in reverse, you can validate the sequence of moves and ensure correctness. Inefficient pattern matching is also a pitfall. Brute force approaches that check every possible stamp placement can quickly become too slow for larger inputs. Instead, optimize by focusing on partial matches and leveraging a queue to track reducible segments. Finally, some solutions stop too early, leaving parts of the target string unchanged. To ensure completeness, always verify that the entire target has been reduced to question marks, avoiding incomplete solutions entirely. Now, it's important to account for edge cases that can break naive solutions. For example, if the stamp is ABC and the target is ABC, or if the stamp is a single character like Z with a target of ZZZZZ, simple approaches may fail. Testing these edge cases is essential to building a robust solution. From an interview perspective, there are a few key insights to keep in mind. One important pattern here is that the problem becomes easier when approached backward, from target to stamp, because identifying valid placements becomes more straightforward. In terms of efficiency, interviewers often expect solutions that avoid redundant work, so aiming for an O, an asterisk M, complexity is ideal, where N is the length of the target and M is the length of the stamp. Using a queue to process reducible regions is a common way to achieve this. Additionally, this problem is a great opportunity to demonstrate your understanding of greedy algorithms and how they can be adapted for challenges like overlapping or partial matches. Finally, make sure to communicate trade-offs in your approach. For instance, reversing the stamping process reduces complexity compared to solving it in a forward direction, and being able to explain these choices shows depth in your problem-solving strategy. This problem also shares similarities with several related problems that can help you build your skills further. For instance, LeetCode 791, Custom Sort String, focuses on reordering strings based on a custom pattern. Then there's LeetCode 1044, Longest Duplicate Substring, which involves optimization challenges in string manipulation. LeetCode 140, Word Break 2, requires you to construct solutions from smaller segments, much like breaking down a target string. Lastly, LeetCode 30, Substring with Concatenation of All Words, deals with matching patterns within a string, presenting similar conceptual challenges. When it comes to alternative approaches, the greedy method of reverse stamping is an effective choice. By working from the target string and replacing matches of the stamp with question marks, you can trace the sequence of moves more easily. However, this approach requires careful handling of overlaps, which can add complexity. Another option is to use dynamic programming. Here, you can compute the minimum number of moves needed to reduce the target. While this approach provides a rigorous solution, it does come with increased space complexity, so you'll need to weigh that trade-off. Finally, a brute force approach can be used as a fallback, but it comes with significant limitations. In this method, you try every possible placement for the stamp and backtrack if necessary. While it's a straightforward way to explore the problem, it quickly becomes inefficient for larger inputs due to the exponential growth in complexity. This makes it unsuitable for cases with long target strings or numerous stamp placements. While it's important to understand brute force as a conceptual starting point, optimizing beyond this approach is crucial for real-world scenarios in competitive coding environments. Great job! We've successfully tackled LeetCode problem number 936, stamping the sequence. By using a greedy approach, we efficiently solved the problem while keeping track of visited indices. Remember to practice similar problems to sharpen your skills. Thanks for joining me, and I'll see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!